This is our first of the gas law lessons. This lesson is on Boyles' gas law, the volume pressure relationship. Show you what happens to gases as the volume of a gas is changed, and see what happens to the pressure of that gas. We've got a little simulation here. We're going to run, and we're starting with an initial 3. The gas particles right here are bumping into each other and colliding with the our values in. The simulation runs its course. It stops when it hits pretty much an equilibrium, and we're going to quickly write down our values. So 0.32 for a volume of 3 liters. And we're not going to worry about what units of pressure. Next up, we're going to double the volume and see what happens. And we can right away see that there's greater space between particles. There's greater space between particles. That's going to mean it'll take longer for them to make their way over to the wall of the container to collide with it. And so that means there'll be less collisions along that wall, and that will decrease the pressure, which is what we've seen here. So we initially started with a pressure of 0.32, doubled the volume, and now we can see that our pressure has been halved to roughly around 0.15, maybe 0.14. Next, what we're going to do for our third point is we're going to decrease the volume. And what we'll do is we'll half the volume from what it initially started at. So we initially start at 3, and we're going to bring it down to 1.5. Right away we can see that the gas particles are now crammed into a much smaller space, so I'm sure we could infer what's going to happen to the pressure. Remember, pressure is dictated by a number of collisions and the force which those collisions hit the side of the wall of the container. And by decreasing the volume, we can see we have much greater frequency of collisions hitting the side wall, which translates into greater pressure. And our pressure here is much greater. We have the volume, and we more than doubled the pressure from the initial test at 3 liters. So what we're going to do is switch over now and take a look at Boyle's law and try and determine what relationships there are with Boyle's law. So Boyle's law looks at the relationship between volume and pressure, and when we did our initial test, what we found was that as the pressure, or as the volume decreased, the pressure greatly increased, and what we got was this neat little curve here where we've got this what we would call an inverse relationship, where if one thing goes down, the other thing increases. And in fact, what we've done here to give us a nice solid line is we've taken the pressure values and we have inversed them. So we've taken 1 and divided by the pressure, and we flipped it, inversed it, and now we get this relationship with a nice linear line. So any pressure value that we had for these points, what we did is we took it and we said, well, 1 divided by pressure 1 gives us, and we'll say in this case it gives us something like 0.0004, and we did the same thing. And so now we get this interesting relationship where the inverse of the pressure gives us a nice straight line. So what does this tell us? Well, the relationship here is an inverse relationship. So if volume goes up, then pressure must go down. or if pressure goes up, then volume must go down. And so if one does one thing, the other does the other. Now, we're not satisfied with leaving it like this. We would like to make some, be able to make some predictions. One thing we have to identify is in this graph, we're going to use this graph to help us develop our model. And what we notice that along the line, because we have a nice straight line, we have a set slope. So the ratio of volume to the inverse of our pressure is always going to be the same no matter where we go along this line here, which is going to be really important. So the slope of the line, we have a straight line. So a straight line means a constant slope. That's going to be really important in a second. So what we're going to do is we're going to start with the equation of a line, y equals mx plus b. And we're going to try and derive a mathematical relationship between volume and pressure. So what we can do is we can sub in our variables. So our y variable is volume, and our x variable is 1 over p. It's not p, it's 1 over p. Now, because we go through the y-axis, b, our y-intercept, equals 0. So we can get rid of that. And our m is our slope. And remember, our slope is constant. So we get then y equals m 1 over p. Now we want to get m by itself. So in order to get m by itself, we multiply both sides by p. And by doing that, we can cancel that out, and we get PV. So P times V equals M. So what does that mean? That means anywhere along this line, the relationship between my pressure and volume, if I take my pressure and multiply it by my volume, it will always give me the same answer. So if I start with an initial state where I have a pressure and a volume reading, and then I change that, I will always get the same thing. If I multiply my pressure and my volume, I could change it again. And it doesn't matter. Whenever I make a change to one, it will affect the other, so that by multiplying these two values together, it will always be the same no matter what. So if my pressure increases, then my volume must decrease in order to keep my slope the same, to keep it constant. We use a small k to denote a constant. So now we can apply this to some questions. This relationship, P1V1 is equal to P2V2. And it doesn't matter. You could say V1P1 is equal to V2P2. That doesn't matter at all. So let's take a look at some questions here. We've got a problem where we've got a weather balloon. It's got a volume of 2,000 liters, and we know what the pressure it is, and it's an altitude. We know that when you go up in the air, air gets thinner, so obviously the pressure is going to decrease. So it goes up 1,000 meters, is only 60.8 kilopascals. So we've dropped by 36, just 6 kilopascals. And if we have no change in temperature, which there really would be, but we're going to pretend there isn't, determine the volume of the weather balloon is. And this is important because if your weather balloons have a certain amount that they can expel, you want to make sure that you use so that they don't expand too much and then pop, and then there goes your weather balloons. P1 V1 is equal to P2 V2. Well, we know that we have an initial pressure of 96.3 kilopascal. We have an initial volume and we have a final pressure of 6.0 pascal. We're looking for our final volume. So our relationship P1 V1 is equal to P2 V2. Now we want to find V2. So in order to divide, and those guys will cancel out, and we get V2 P1 V1 over P2. So we'll just write that right here. So now let's develop our solution. And we'll plug in our values. Always make sure we put our units in. Now we hit our calculator determinant. Remember to go down, then volume must go up. And in this case, because of the inverse relationship, and we know it's greater, therefore V1 must be smaller than V2. They're doing the opposite. See these signs going the opposite? It looks like at our final pressure, sorry, V2, put the wrong thing in there. That should be volume. Should be greater than the initial one of 2,000 liters. So we now type in our calculations, 96.3 times 2,000, 8, and we get 3,167.8 liters. Scientific notation, we'd write at 7 10 to the 3 liters. So what we're going to do at this point is giving you a couple questions. You can pause to write these questions out. I'll pull back the curtains and give you a chance to see if you got the correct answer. So take a second to pause and write that out, and then I'll take it up. Look, our first, we have a liter of gas at 1 atmospheric unit pressure, and it's compressed down to 0.437 liters. So what is the new pressure of the gas? Well, if we know we're compressing a gas, obviously we're adding an increase. Let's take a look at this right now. So we write out our values, what we know our values are, P1 V1, P2 V2, don't know what P2 is, and we'll the solution. I set up my equation. In this case, I substituted my values in before I manipulated the equation. Whatever you want to do, that's up to you. Do whatever makes sense to you. You can rearrange before, or you can substitute in. Doesn't matter. So in this case, we get 2.29 atmospheres, which is definitely greater than 1 atmosphere, and we was in half. So that would mean our pressure would have to be increased, be more than double. So there we go. We have another question here. We have portable air compressor, has an air capacity of 15.2 liters and 210. If all the air in the tank is released, what volume will that air occupy at atmospheric pressure? Now this question, we've been throwing a bit of a monkey wrench here. We've got one form of pressure unit. So our first step is going to have to be to convert or to change our units of pressure over. So that's what I did with the first one. I decided to keep this with PSI. Just chose to do it. You could have converted it to kilopascals. Converted P2 to PSI. So we notice here that we from 110 PSI down to 14.8. So P1 is much greater than P2. That would have to mean then that V1 is smaller than V2. It'd have to be the opposite. If this is big and this is small, then this has got to be small and that's got to be big. And we'll take a look and see what the calculations, what we got for our answer. So I did my equation, I manipulated it to solve for V2, so what I did up here, and I plugged everything in, and look at that, 113 is greater than 110 is much greater than 14 or 15 roughly. So you can see that there's been a great change in volume, which makes this concludes the lesson on Boyle's law, which deals with